Hello, folks. So this is your first video in section 2 of Unit 8, talking about hypothesis tests for means. So really quickly, I'm going to do a very quick review for you about the general basics of a hypothesis test, but then I'm going to jump into the differences that you see between hypothesis tests for means and hypothesis tests for proportions, which you've already learned about in the previous unit. Okay, the process that we're going to use throughout any hypothesis test for means is the same process that we use for proportions, right? It's just some of the formulas are going to change. There's the way you write the hypotheses looks a little different, right? We're using means instead of proportions, etc., right? But everything that you're used to, the process that you follow, the steps that you go through remains the same. Okay, so the important thing, especially when you're dealing with inference, is to know the general process, whether you're dealing with a confidence interval or a hypothesis test, and then be able to remember the little differences at the individual steps for means versus proportions. Okay, so if you want to look at a more detailed review of hypothesis tests in general, you can look at page 9, page 10 of your notes, right, where I do a review for you about vocab, p-values, statistical significance, error, and then I also do an overview for you of the whole process for hypothesis test for means. We're still using our phantoms process, okay, but what I really want to focus on is the changes between means and proportions when we're talking about hypothesis tests. Okay, so really quick reminder for you, remember hypothesis tests can either be one or two-sided. One-sided tests have a less than sign or a greater than sign in the alternate or alternative hypothesis. Two-sided tests have a not equals to sign in their alternative hypothesis. In general, if the p-value, right, which is what you get from your calculator, right, using like in the past, we've used normal CDF, right? If that is below your significance level, your alpha, right? If the p-value, which you get from the test, is below your standard, right? That's the alpha value. You're going to reject your null in favor of your alternative hypothesis, okay? If the p-value is greater than alpha, you're going to fail to reject your null. Okay, remember, you never accept a null. You're just saying you don't have enough evidence from this test, that the evidence that you got is not strong enough to reject the null. Okay, right. And then just another quick reminder for you about error. Okay, error occurs when what the test tells you to do, i.e. rejecting or failing to reject the null, does not match what should happen in reality. Right? That's when an error occurs. Okay? A type 1 error is when you reject the null when in reality the null is true. And a type 2 error occurs when you fail to reject the null when in actuality the null is false and you should have gone with your alternative hypothesis instead. Okay, so let's talk about the differences and the changes that you see when you're doing hypothesis tests for means versus proportions. Okay, like I said at the beginning, you're still using your phantoms procedure. Okay, there's just a couple of differences. Okay, the first, fairly obviously, is that hypotheses are written with means instead of proportions. Right? So an example would be my null hypothesis would be written, say, mu equals, and I have on there 27 minutes, right? And then my alternative hypothesis would be something like mu is, I have on there less than 27 minutes. Okay, so rather than using p here for proportion, you're using mu. Okay, all right. The next thing that is different comes at the A step, the assumption step. Okay, the first two conditions randomness and 10% are the same. The only thing that's different is the success-fail condition, which I'm hoping you're used to this change by now because it happened with sampling distributions for means, and it also happened when we were talking about confidence intervals for means. Okay, but the success-fail condition, or the large counts, large enough sample condition, is n is greater than or equal to 30 now. Okay, so your sample size must be greater than or equal to 30, or you have a normal population. Okay. The next thing that occurs at that's a little bit different is at the name the test step. Okay, here, because we're dealing with means, you're going to use a t-test instead of a z-test, which again, I'm hoping you were expecting a little bit, because this is also what happened when we dealt with confidence intervals for means, right? We were using t intervals instead of z intervals. T goes with means and z goes with proportions. Okay. Another difference occurs at the standard deviation, right? When we're actually calculating our test statistic at the t step. Okay, so the standard deviation of the mean, standard error formula changes. So you don't have to do the p times 1 minus p over n all underneath the square root. Instead, it's the standard deviation of the sample divided by the square root of n. Okay? Exactly the same as the change that happened when we were doing confidence intervals for means. Okay. The last thing that changes is when we get to the O step, which is how we obtain our p-value. Remember, that comes from the calculator, right? Whenever you're doing a p-value, you should get that from the calculator. It makes your life a lot easier. You're used to using normal CDF, okay, or the Z table. So we're not going to use the Z table, and we're also not going to use normal CDF on your calculator, okay? Because I know that's what you all are used to, okay? Instead, okay, what we're going to use instead of normal CDF or the Z table, you're going to use TCDF on your calculator with the degrees of freedom, that's DF, of n minus 1. So remember, your degrees of freedom is always the sample size minus 1. Okay, and you're using that to find your p-value, okay, rather than using the Z-table or normal CDF. Okay, on your calculator, here is how you access TCDF. Just go to a regular calculator page. Okay, click the menu button. I gotta leave myself some space for arrows. Then click Statistics. Then click Distributions. And then the one you're looking for is called TCDF. Okay, and when you do this on your calculator, it's going to ask you for the sample mean, the sample standard deviation, or it'll ask you for your test statistic value, right? And it'll ask you for the degrees of freedom, right? Things like that. Okay. Other than that, everything else remains the same. Okay, so it's these 1, 2, 3, 4, 5 changes, which I know seems like a lot of changes, but like intuitively, I'm hoping a lot of them make sense. And a lot of them, you're just changing like one calculator command, or you're swapping out a standard deviation, right? Writing the hypotheses a little bit differently, etc. Okay, so I have 2 examples for you. I'm going to do the first one, and then I'm going to have you try the second one out. Okay, so in this first example that we are dealing with here, okay. Oh, and by the way, I do have this this written for you on the left side of your screen. When you're calculating your test statistic, right, notice that it's still a lot of the same stuff, right? See how you're still doing a statistic, which is the sample mean, x bar, minus the claimed mean, right, from your null hypothesis divided by the standard deviation. So it's still the same. I'm sorry, folks, my mother is texting me. So it's still the same format as like a z-score, right? This would be like a t-score instead, right? And you're still doing the same things with shading, and when you sketch out what your normal or bell curve will look like, right? You're still shading in the same directions depending on what your alternative hypothesis is, right? You're still rejecting or failing to reject the null based on your alpha value in comparison to the p-value that you get. Okay, so a lot of the stuff is the same, right? So let's talk about this EPA example here, okay? So with this EPA example, okay, and this is a really common thing and that government agencies do in order to protect us, right? This is one way that statistics can be used in like a completely real world setting to the point where it can actually impact the lives of people in the communities. Okay, so one of these is dealing with the EPA. The EPA does this a lot, where they will set a limit on the allowed concentration of chemicals in drinking water, right? Because if you have more than that, then it can get to unsafe levels for people to consume. Okay, so in this problem, we're talking about a substance called PCB, and the limit is set at 5 parts per million. Okay, so in a random sample done by the EPA, they pulled 36 water specimens from the same area, and they got a sample mean of 5.18 parts per million and a sample standard deviation of 0.6 parts per million. So the question is there sufficient evidence to claim that this particular well has water that's unsafe? Okay, and they're telling us to use a 0.01 level of significance. All right, so we're going to go through our phantoms procedure. Okay, so remember, P stands for parameter, right? What are we actually trying to determine here? What are we actually examining? So we are estimating the true mean PCB concentration in the drinking water. Okay, all right. Now for my hypotheses, okay, obviously we're going to go with the claim here, and the claim is that that the water is fine, right? We're going to operate under the assumption that the well water is fine, which would mean that the mean, the true mean, is 5 parts per million. Okay, but we're trying to test to see, is it unsafe? Okay, meaning what we're trying to prove is that the mean is actually greater than 5 parts per million. Okay, all right. So next, let's do our assumptions. Okay, so the first is this a random sample? And yes, that was stated in the problem. So remember, you can literally just say SRS stated in problem. Okay. Next, 10% condition. We have to check, is the population larger than 10 times the sample size? So I'm going to do 10 times the sample size, which is 36. That's 360, and that's definitely less than the total possible water specimens. Okay. And then the last thing I have to check is the large enough sample. So remember, for large enough sample, we either need the population to be normal, which we don't know, they don't tell us here, okay, or my sample size has to be greater than or equal to 30. And it is in this case. My sample size is 36, which is obviously greater than or equal to 30. So I'm all set there, right? Okay. Next, we have to name the test. Okay, so remember, there's a couple of questions that you ask yourself. Okay, the first question is, how many samples are we dealing with? Right, and we're dealing with one sample. Okay, so this is a 1, and then are we dealing with means or proportions? Okay, and this is means. So this is a 1 mean, and then is it a Z or a T test? And this is a T test. Okay, you will also sometimes see it called a 1 sample. t-test. Okay, they mean the same thing. Right? And then the other thing we have to do here is set our significance level. And they do tell us in the problem, they want our alpha value to be 0.01. Okay. All right. Next comes the actual math part, right? T and O are where the actual math steps happen here. Okay, so my mean that I'm assuming that I'm dealing with for the population is 5. Okay, X bar is 5.18, right? They tell us that in the problem. Okay, and then the sample standard deviation was 0.6. Okay, so I need to use that to find my new standard error, right? So I'm going to take my standard deviation from the sample, 0.6, and divide it by the square root of n, which is 36. So 0.6 divided by the square root of 36 is 0.1. Okay, so in my test statistic, right, I'm going to use 3 different things. Okay, so this is my statistic. This is my parameter. And this is the standard deviation that I'm going to use. Okay, so those are the 3. Sorry, folks, hold on. I'm drawing over things here. Okay, so these are the 3 things that I need in order to do my test statistic or my t-score. Right? Okay, so t here is 5.18 minus 5 divided by 0.1, which is, when I do all that math, is 1.8. Okay, and the last thing I need to do here for myself is say, oh yeah, I need my degrees of freedom because I'm going to need that for the next step. So degrees of freedom, remember, is always sample size minus 1, so 36 minus 1, which is 35. Okay, all right. Next, we have to obtain our p-value. Now remember, I write this in a couple of different ways. You do not have to write this the same way that I do. Like, you don't have to write both sets of probability notation here. You can write one or the other. It doesn't really matter. Okay, but at this O step, it is imperative that you write at least one of these probability notations. Either we're finding the probability that the mean is greater than 5.18, okay, or you can write, we're finding the probability that t is greater than 1.8. Okay, one or the other. You don't necessarily have to do both, but you must write at least one, because otherwise the number that comes after it has no meaning, has no context at all, right? Remember, statistics is the math of context, right? The numbers have to have a meaning, otherwise, like, what's the point? Right? And the reason you have to do that is because the AP readers know that at this step, especially this O step, the calculator is going to do most of that work for you. Okay, so you have to show the AP readers that you know what you're talking about. Okay, that this number that pops out of your calculator is this probability that we're looking for, the p-value. Okay, so I plugged this into my calculator in order to get this number, 0.0402. Okay, so I followed this calculator path right here. Okay, I went on my TI Inspire, clicked the menu button, hit statistics, distributions, and TCDF. Okay, and I plugged in my t value, the 1.8. Okay, and I plugged in my degrees of freedom, right? And then it spat this number out at me. Okay, all right. We're very close to the end here, so the next thing we have to do is make a decision. So my p-value was 0.0402. So that's my p-value, but that is greater than my alpha value that I set, which was 0.01. Okay, so what that means, right, the decision that I make if the p-value is greater than alpha is I'm going to fail to reject the null. All right, very last step is I need to state my conclusion in context. So this is where you're going to use your script, use your word formula, okay, and just fill in the blanks with the context of this particular problem. So we would say because the p-value is greater than alpha, we fail to reject the null. Then you would say there is not enough evidence to support HA, which states that the true mean, I really cannot spell today. Oh my gosh. The true mean PCB concentration is greater than 5 parts per million. Okay, and then I put in layman's terms, essentially, we don't have enough evidence to say that the water is not safe. Okay, so we're not straight up claiming that it is safe, right? Because what if we run, and this is a good reason and a good example to show you why we always fail to reject a null rather than accepting a null, right? Because we could run another test, right? Or if I had set a slightly different alpha value, I could do another test that would show that the water is not safe, right? So we're saying we don't have enough evidence to say that the water is not safe, right? Which is kind of using a double negative, right? But that's kind of what you have to do when you're failing to reject a null, right? Because like I said, we could run another test that would give us enough evidence that the water's not safe, right? So if we just straight up accept the null hypothesis, that would mean there would be no reason for me to do any more tests, right? And people could get hurt if that happened, okay? Now, the very last thing on here, I'm going to do as a review for you of error, okay? So it says, describe a type 1 and type 2 error in this context, and which is worse in this case, okay? So remember, a type 1 error always occurs when we reject the null, when the null is actually, or when the null is true, rather, when, I'm going to say, write it like this, when in reality, the null is true. Okay, so what that looks like in this context, is that we would say that the water is not safe, right? That's rejecting the null. We say the water is not safe when in reality, it is safe. Okay, and so the consequence here, if I can spell, my gosh. So the consequence here would be people go without water, right? Or maybe they have less water, okay? So that's a possible consequence. A type 2 error occurs when we fail to reject the null, when in reality, the null is false. And we should have gone with HA instead. Okay, so in the context of this problem, if we're failing to reject the null, that means we're going to go with the null, which is sorry, I don't know why this has suddenly gotten so much smaller. Okay, so in the context of this problem, what that means is that we're going to fail to reject the null. So we're going to go with the null for now. So we say the water is safe because that's what the null says, right? When in reality, it is not. Okay, so the consequence here is that people drink poisoned water. Okay, which I don't know about you, but in my personal opinion, this is worse, right? Because we can always get people water from somewhere else, right? Uh, but a type 2 error here is kind of what happened in Flint, Michigan, right? When we end up with this water that's really not safe for people, right? So this is a real life consequence of making a statistical error, right? So remember, as the statistician, you have the ability to choose how much of a type 1 error or a type 2 error you're willing to accept, right? So and you set that based on your significance level, right? That all comes down to your alpha value that you set, right? So if I want to minimize a type 2 error, I have to make the type 1 error a little bit larger. So in the context of this problem, I probably would want to minimize the type 2 error, which would mean I would need a slightly larger alpha value, right? Okay. On the AP test, you probably could make an argument either way, but in the case of this problem, I don't know. I don't see an argument that type 1 is more severe. I think definitely type 2 is worse in this case, but that would be an interesting debate if you see it a different way. So I'd love to hear your thoughts if you are seeing this a different way than I am. Okay. All right. So we've got one more problem here that I want you all to give a try on your own. Okay. So I'm going to go ahead and pause this video here. And I would like for you to do the same. Okay. Try out this problem about pineapples and then check back with me to see how you did. Really quickly, folks, I didn't realize that there was a typo in your notes up here. So in the notes, it says that the standard deviation of the sample was 2.394. Okay, that should be 2.934. Okay, sorry about that. So if you've unpaused and have done the whole problem, you may have gotten a slightly different answer than I did if you used the standard deviation that's here. Because I don't think I will have time to change it before a lot of you make copies of this notes document, okay? So just make sure that you followed the same process that I did, even if your numbers are a little bit different. Okay, so I need to finish working this problem out on my end. So I'm going to pause again, have you do the same, and then check back with me here to see how you did with the complete problem. All right, everybody, so go ahead and check your answers against mine here. So in this problem, we're talking about the mean weight of pineapples harvested from a really large field. Okay, we're assuming that that weight is 31 ounces. Okay, and they've changed something. They've introduced a different irrigation system, and they want to see if that in fact changed the mean weight of the pineapples produced in this field. Okay, so the key word here in determining what your hypotheses should be is that word changed. Okay, they don't necessarily want to know if the new irrigation system made the pineapples weigh more or if it made them weigh less. They just want to know if there's a change, which means that your hypotheses should have a not equal to sign in them. Okay. All right, so for parameter here, we are estimating the true mean weight of pineapples harvested in this field. My null hypothesis is that there has been no change, so the mean weight has stayed at 31 ounces. My alternative hypothesis is that the mean is now not equal to 31 ounces. I don't care if it's more or less, I just want to know if it's different. Okay. For my assumptions, this is definitely a random sample. They state it in the problem. They say that they select a random sample of 50 pineapples. Okay. 10% condition, is the population larger than 10 times a sample? Yes, it is, right? Because you do 10 times the sample size, so 10 times 50, which is 500. That's definitely less than the total population of pineapples, because they say that we're dealing with a pretty large field here. Okay, and then my last condition is this a large enough sample? And yes, it is. My sample size is 50, which is definitely greater than or equal to 30. Okay. For my end step, I'm naming my test. You could have called this a one mean t-test, or you could have called it a one sample t-test. Okay, one or the other, either is fine. Okay, and they did not give us a significance level here, so I'm going to set my own at 0.05, because that's the most common significance level if they don't give you one. Okay, then I'm on to the actual math part of this. Now, if you didn't go through and change the standard deviation, sorry about that, your answer may be slightly different than mine, but you want to make sure that the process you followed is the same. Okay, so for my test statistic here, the parameter is 31, so mu is 31. My sample mean is 31.935. They tell us that in the problem up here. Okay, and then they tell us that the standard deviation of the sample is 2.934. Okay, so first thing I need to calculate is my degrees of freedom, which I'm going to need in the next step. So degrees of freedom equals 50 minus 1, which is 49. Okay, and then the last thing I need to calculate is the standard error of for my test statistic here, for the sampling distribution, right? So remember, I do that by taking the standard deviation of the sample and dividing it by the square root of n, the square root of 50. So I end up with 0.415. So the three things that I need for my test statistic are this standard deviation, my mu, and my x bar. Okay, those are the three things that I need. So remember, it's x bar minus mu divided by the standard deviation. And so I got 2.253. Now again, if your standard deviation is a little different than mine, then that means this number is going to be a little different. The process is what matters. Okay, now the O step here is where a lot of people mess these up, especially because we're dealing with the not equal to sign here. Okay, so check this part carefully, all right? So remember, we are trying to find the probability that mu is not equal to 31. We're trying to see how likely is that. Remember, when you have a not equal to in your hypothesis, right, what that actually looks like when you sketch it out, okay, is it looks something like this, right, where this is two-tailed, okay? Okay, so the way that you can figure this out is you can find either the probability that t is greater than the positive version of your t score, so 2.253 for me, or you could say what's the probability that t is less than the negative version of your t score, so either greater than the positive version or less than the negative version. You're going to get the exact same number either way because these are symmetric, right? So you're going to get the same area, right? The same probability on either side, okay? And whichever one you find, you have to multiply it by 2, right? That's what this is, because this is a two-tailed test, right? If you only find, for example, this one area, the t is greater than 2.253, that's only this part, right? You have to also include this part. Okay, that's why you have to do whatever probability you find times 2. Okay, right? So when I plugged this into my calculator, one or the other, you don't have to do both, I got that value, the greater than 2.25 or less than negative 2.25 was 0.0144. So I'm going to take that value, multiply it by 2, and this is what I got, 0.0288. Okay, since this p-value is less than my alpha value, I'm going to reject my null. okay? And then I'm going to state my conclusion in context. So because my p-value is less than alpha, we reject the null. We would say there is enough evidence to support the alternative hypothesis, HA, which states that the true mean pineapple weight, which is what your parameter is up here. That's why I make you write the parameter at the start. Okay, so true mean pineapple weight is not equal to 31 ounces. Okay, you're basically just writing your alternative hypothesis in word form. Okay, and then I put a little IE here just to put this in layman's terms. So IE, the pineapple weight has indeed changed. All right. Okay, so that is it for this video. There's another quick video for you in this section on how we connect hypothesis tests and confidence intervals, and then another one that's a little bit longer on paired t-tests, okay, which sound very new and different, but actually are very similar to these one proportion, or not one proportion, these one mean t-tests. All right, so whichever video you're watching next, I'll see you in the next one. Bye, everybody.